Hi. So the next thing we want to talk about is volume. Now we talked very in depth about the area in Calc 1, where you sort of develop this idea of breaking your area into smaller pieces, sort of smaller intervals, and then defining things that you know the area of on each of those regions, and then adding all of those up, and then sort of limiting this area or the sort of width of each of these pieces to 0. So you sort of say, I've got my shapes, oops, and then I'm looking at my function, and I want to say there's some area underneath that curve. I break my region into smaller subintervals, and then on each of those subintervals, I define a rectangle, because it's nice and easy to find the area of a rectangle. That's a very sort of easy thing to do. And so what I do is I say, oh, well, I can find the area of that rectangle. And then the smaller those regions are that I break this into, the kind of better the estimate is of this area. And so if I take that sort of small region, small area, the small width that I've got for each of these rectangles, and I take that width to 0, what I actually end up getting is the area underneath the curve. Okay, so that's how we sort of developed the area as an integral underneath a curve with this sort of delta x, this small x area distance that I multiplied to give myself the area of the rectangles of which that I'm breaking this into. So I want to do the same sort of thing now. This time I want to think about volume. So there's sort of really two ways to do this. And so the first way I want to do this is I want to think about a three-dimensional object. And so you can sort of think, you've got some sort of three-dimensional object, and I can define it as sort of being with a base that's a function. And then I want to think, if I cut that three-dimensional object with a knife or with like a pastry cutter, maybe a better thing, what is the shape that is left on that knife or pastry cutter? What's that shape look like? And if that shape is nice enough, I can find the area of that shape, bump it out a little bit, make that have some volume, and then add up all of those volumes to give me an estimate of the area of this three-dimensional object. Okay, so that's the way we kind of want to work here. And so what I might start with is I might say, hey, we have potentially maybe a sphere. So if I think about a sphere, and I think about taking my knife or my pastry cutter or whatever it is, and I sort of slide it into this object, I kind of slide it in here and I cut it and I pull it out. I look at the side of it and see what the shape is of that the cake left, or whatever this thing is left on the knife or pastry cutter or whatever it is. So I can cut it in several different places. And what I will get in this case for a sphere is all of these little sort of side slices will be different circles, each with a different radius. Okay. And then I say, oh, that's great. Now I bump out a little bit. And when I say bump out, what I'm really sort of saying is give that a little bit of width. So give this a width of like delta x. And now, instead of just being circles, these things are like little cylinders. And so then I have sort of the volume of that little cylinder is easy to calculate. And then I can work from there to find an estimate of the volume of the sphere. Okay. Then I let that width, that delta x, go to 0. So I take that limit as that thing sort of gets smaller and smaller and smaller. That gives me a better estimate, a better estimate, better estimate. Eventually, that is going to give me the exact volume of this sphere in the limit as that delta x is going to 0. So that's the sort of big idea here that we want to do. So what we want to do is sort of break this three-dimensional object into slices, take the volume of each of those slices and add them up. Well, luckily for us, all that really matters about this is the cross section, and each of those cross sections has an area. So all we care about is the cross-sectional area of this object. And so then that we bump out using this delta x, giving me the three-dimensional sort of volume object, and then I can cut it from there. So that's kind of what we're thinking about here. I take my cross section, I look at the area of that cross section, multiply it by delta x to bump it out to make it a volume, and then add up all of those cross-sectional areas, end up taking the limit, which ends up being an integral instead of a sort of area, right? So we're going to think about this a little bit. So here's an example. So I'm gonna look at an object. It's going to be formed with a base x equals 0, y equals 0, and 1 minus x squared as the base of this thing. And each of the cross sections that I take perpendicular to the x-axis are going to be squares. So I sort of think about this object a little bit here. So what I have is I have the x-axis, the y-axis, and a parabola, 1 minus x squared. So 1 minus x squared is a parabola. It's been shifted up 1. I mean, it's sort of not well drawn there. That's always good. So I just do that. So this is the object I'm thinking about. And I want to look at the base of this three-dimensional object on top of this. So the three-dimensional object on top of this has a base that's bounded by the x-axis, the y-axis, x equals 0 and y equals 0, and then this parabola. Okay, and now I think about the three-dimensional object on top of that. I cut it down into that, and each of these sort of slices will look like a different sized square. So each of these are going to look like different sized squares. And so each of these sort of cross-sectional areas here is a square. So there's squares, some smaller, some bigger, that all lie out here. And in fact, the very sort of last squares down here at the bottom are going to have really small side lengths, and at this intersection point, the side length is 0. So you're kind of going from a square that has side length 1 down to a square that has side length 0. Cross-sectional areas. Now I bump those out a little bit with a delta x. That makes it a volume. And then I take that volume, add them all up, and essentially turns it into take that limit. That makes it the integral of the functions. All right. So with that, I can sort of say, oh, well, in fact, I have these sort of side lengths, these squares that have side lengths going from 0 to 1, with the given by the y value of the function 1 minus x squared. And so the side lengths are technically 1 minus x squared. And so the cross-sectional area is that squared, because the cross sections are each squares. So each side of this square is 1 minus x squared. So the area of that square is 1 minus x squared quantity squared. Okay. Now I take that and I add them all up, and that gives me the integral. And so that gives me the volume of that parabolic cube as the integral from 0 to 1 of 1 minus x squared quantity squared. And I have to FOIL that out to sort of make it so I can actually do that integral, since I don't have any x term outside of that, can't do u substitution. And then I integrate, evaluate between 0 and 1, gives me 8/15 as the volume of this parabolic cube, which is kind of cool. All right. So this works really well. We can kind of do this as long as we know what the cross-sectional area looks like. And now we're going to look at two situations where we have a very special cross-sectional area. So the first one is rotation of a curve around an axis. And so if I think about a curve, a function f of x, we could just do, again, the same, maybe x squared this time. And if I rotate this now around the x-axis, what I end up with is this sort of conical shape. And I might go from, say, 0 to 3, and I get this sort of conical shape. And I want to know what is the volume of the cone, the conical shape, maybe it's like a parabolic cone, formed by rotating x squared about the x-axis between 0 and 3. So what we can do is actually just thinking about this again. I take that cross-sectional area. Each of the cross sections that I get is going to be a circle, and that circle has radius that's equal to x squared. So each of the x's gives me a different radius of these things. I bump them out with the delta x and I go from there. Now that's nice in particular, because every time I rotate any function about the x-axis here, I get the same cross-sectional area. So that same cross-sectional area will work for each of these. So if I think about this, we end up with the cross-sectional area of a circle, and the area of a circle is pi r squared, and that radius is given by the function value. And so thinking about our picture again, if I've got my x squared here, you know, the radius is going to be the function value at any given x value. And so as we sort of go from 0 to 3, that will change. But then I swirl this around the x-axis and it becomes a circle with that exact radius. And so this is really good. So basically, I end up with a formula for any time I rotate around the x-axis here. This is pretty cool. All right. Well, unfortunately, I sort of get into a little bit of trouble here because I don't just have like one axis I can spin this thing around. I actually have more than one axis I can spin this thing around. And so I can spin this thing about not only the x-axis, but also maybe about the y-axis. So the question is, what happens now if I try to take this x squared and I try to rotate it around the y-axis instead? Well, now we're kind of in a little bit of trouble because I instead of having cross sections that are circles, now the cross sections are going to look a little messy. So the vertical cross sections of this thing are awful, but the horizontal cross sections of this are circles. So what I need to do here is I need to change my frame of reference. So just like we did when we had like the area between two curves, it's possible to take and switch those x values to y values and then cross-cut these sections horizontally rather than cross-cutting them vertically. So parallel to the x-axis rather than perpendicular to the x-axis. And so what I'm sort of saying here is we basically can take my y equals x squared function, solve for x, gives me the x is the square root of y, and then I can take the volume of this thing that's now swirled around the y-axis rather than about the x-axis. So I'm going to swirl around the y-axis. In that case, when I'm swirling around the y-axis, I want to integrate with respect to y. And so what I might say is I'm going to sort of integrate from 0 to 9. So that'll give me the same intersection point here with the 3. And then I'm going to integrate. It'll give me the same cross-sectional area. It's just pi r squared, and the r in this case is going to be in terms of y. And then I bump them out a little bit with like a little delta y, and then I integrate, making that delta y sort of disappear. So I'm going to integrate that delta y to 0, so no width of these things, and that's going to give me the exact volume of these. And so I end up with pi times that squared, pi r radius squared, and then delta y. And so now I can integrate that thing just fine. Things work out, gives me exactly what I need. In this case, it just gives me y squared over 2, and then pi times y squared over 2, and then evaluate it between 0 and 9. And so I really get 81 pi over 2 is the volume of this bowl shape. It's like the parabolic bowl shape that I get by revolving the parabola around the y-axis. Okay. So changing our frame of reference is very convenient, and sometimes it's possible, sometimes it's not. And in particular, when it's possible, sometimes it's easier to integrate that shape with respect to y. And so that's kind of nice. All right. So this is really great. So we basically have like two rules that we can work with. If I'm revolving about the x-axis, I want to use the top one of these. And so I'm revolving about the x-axis. I'm going to have cross-sectional area of circles. And notice I can actually do this with like an outside and an inside function. So rather than just getting like an outside function, I can revolve this whole thing around. And instead of getting a circle, like a disk, what I actually get is like a washer. And so it's possible to have like a top function and a bottom function. And so about the x-axis, if I have a top and a bottom function, I just take the volume of the outside thing, which is the top function, minus the volume of the inside thing, which is the bottom function. I sort of pull that piece out. It's like a child like pulling cake out of the middle of the cake. You sort of grab that and pull that out of the middle, and the volume of what's left is going to be given by the integral of the first squared minus the second squared. So you're sort of taking and pulling out the second piece, the middle piece, and taking the outside piece minus that inside piece. All right. And so about the x-axis, that's what we do. About the y-axis, same deal. This time this is the top, and this is the sort of rightmost function. And then the g is the bottom, or it's the left function. And so if you sort of graph f and g, you can sort of see which one's the top, which one's the bottom, which one's the right, which one's the left, as you're sort of looking at the graph. All right. So this is great. We really have a lot of things that we can do with this volume calculation. Unfortunately, there are situations where I cannot actually do this. So in particular, let me just give you an example. And this is a motivating example for what's next here. I want to take sine of x squared, and I want to revolve it about, the y-axis. And so I take this sine of x squared, revolve it out the y-axis, and I might even take for x from like 0 to, let's go for the square root of pi over 2. So that way it's going to be from the bottom of one period of this sine up to the top of one period of this sine, from sort of 0 up to the top of the periods. So 0 to 1, and then we go from there. We take that and we revolve it about the y-axis, and we want to know what's the volume of this thing. Well, unfortunately, what we would have to do using the stuff we did this time is we would have to switch x and y, basically solve for x in this equation, which in that case, what I'm looking at is the inverse sine of y under a square root is equal to x. Now I am supposed to apparently integrate this thing, and I do not know the integral of the inverse sine of y. And in particular, we have not learned that. We aren't there, right? So this is something I cannot actually do, is to find the integral of the inverse sine of this. So there's got to be another frame of reference that we can use to figure this out, and there is, and that's what we're going to do next in the next section here is what's called the shell method. So instead of breaking these things up by cutting them into sort of cross sections, what I do is I actually think of it as like break them into little rectangles and then revolve the rectangles around. Those little rectangles carve out shapes that we would call shells, and then let those little rectangles go have width of 0 eventually, and that's going to give you more and more shells to give you the exact value of the area or the volume of this thing. And that's nice. What's nice about that is it allows you to integrate with respect to x when you're revolving about the y-axis. So that's really good. So in this case, that's going to be good for us because I can integrate sine, no problem. I cannot integrate inverse sine, and so that we're going to be in trouble there. All right, so next time we'll talk about that in that next section. All right. Go on, try that homework. I think it's not too bad. Let me know if you have any questions. Thanks, we'll see you.